Hello, let's continue looking at some trigonometric integrals. In the last video we looked at integrals of the form sine to the n of x times cosine to the m of x dx, where n and m were constants. In a similar manner, we're going to look now at integrals of the form tangent to the n of x times secant to the m of x dx. And they work a very similar concept, similar way to what we did before with sines and cosines. The key, again, is to make a substitution for u so that we have what we need for du. In addition, we also need the other part to be an even power so that it can be transformed into a function of u by a Pythagorean identity. That's what we did last time. That's what we're going to do this time. This time, the Pythagorean identity is tangent square of x plus 1 equals secant square of x. And let me also remind you the derivatives that we need. The derivative of tangent of x is secant square of x, and the derivative of secant x is secant tangent of x. So if you look at this, if you've got an odd power of secant and tangent, we can bring out, we can let that be part of the du, then we let u be the secant of x. And then that'll work as long as the tangents, powers of tangent that are left are even. We can use this identity up here to switch them to secants. And similarly, if we have an even power on secant, we can bring that out, secant square out. We'll be left with an even power of secants, and we can change them to tangents. We're letting u be tangent of x there. So if the power in secant is even or the power in tangent's odd, we can use that basic setup. So those are our first two cases. So if m is an even natural number, we split off even power on secant, that is. We split off a secant square to be part of du, and we are left with an even power on secant of x. Let u be tangent of x, and thus du is secant square of x dx. And we use secant square of x equals tangent square of x plus 1 equals u square plus 1. So that allows us to change the secants into functions of u. So we've got an algebraic function, probably a polynomial function of u to integrate. Case 2 is n is an odd number, that is, we have an odd power on the tangents. We split off with one of the tangents with the secant to be the du, and that will work if we let u be secant of x, then du is secant of x tangent of x dx, and this will leave an even power on tangent of x. We use tangent square of x is secant square of x minus 1, or in other words, it's u squared minus 1. And again, this will give us an algebraic function. If the m is 0, that is no secant factor and an even power on the tangent, n is even, m is 0. In this case, you factor out two factors of tangent of x and convert to tangent square of x plus 1 equals secant square of x minus 1. That's not right. Tangent square of x equals secant square. There's an extra plus 1 right there. Let me get rid of that. There we go. And distribute and repeat is necessary to get one of the forms above. If m is an odd natural number and n is 0, so there's no tangent factor, and we got an odd power on the secant, you can integration by parts with u equals secant of x. And it's a little bit of a tricky way to do that. There's an example in your textbook. So in the textbook that we're using, at least, it's example 6 in section 8.2 of Larson's text. And I don't plan on asking one of those probably in my class. And if you can't get anything else to work, when all else fails, switch everything to sines and cosines and see what you could do at that point. Maybe you can get one of the previous techniques from the last section to work. So here's an example of this. Tangent to the 40th of x times secant to the 4th of x. So we have an even power on secant. So you can get a secant square stripped off to be part of the du, leaving an even power on secant that we can switch to u if we let u be tangent of x. So let u be tangent of x, du is secant square of x dx. Then secant square of x is tangent square of x plus 1, or in other words, u square plus 1. So when you split off one of the secant squares with the dx, that's right here becomes the du. We're left with the secant square of x, which is u squared plus 1, and then the tangent of x is u, so this is u to the 40th. Oh, now it's easy. You just distribute the u to the 40th, and we got a nice little polynomial, just two terms. Just use the power rule. Add 1 to the power, multiply by the reciprocal of the new power, so that goes to 1/43rd u to the 43rd, plus u to the 41st times 1 over 41, and then plus c. And then switch back to u's. U is from u's to tangent. Actually, before that, I'm going to do a little factoring. So what I've done here is sort of get a common denominator, 41 and 43. The common denominator is 41 times 43, which is 1,763. So I've factored that out, and I've also factored out a u to the 41 out of these first two terms. Now, what does that leave here? Well, when I divide u to the 43rd divided by u to the 41, I get u squared, and then, of course, this cancels out completely on this one. So what I'm really doing is dividing by this right here means I'm multiplying by basically by 43 and a 41. The 43 cancels here, leaving a 41. The 41 cancels here, leaving a 43. So that sort of gets us all our fractions sort of in one thing. That's basically the same thing as getting a common denominator. I could write as one big fraction with that as a denominator if I wanted to. Of course, we still have our plus c at the end. Let's go ahead and change back to tangents, back to x, which is u is tangent of x. So this is tangent of x to the 41st power plus 41 tan square of x plus 43, close parentheses, and plus c. So that's our final answer. And just as a check or in an illustration as well, I put this in my GeoGebra app, and there's the antiderivative. It's basically this form right here with the u's changed into tangents, which is what we have here. And we can see the graphs. The original graph is in blue, and it kind of comes down and back up. And then the other ones are right here for the antiderivative that we're looking at. Of course, c is 0 at the moment, but you could shift it up or down by changing the value of c. Let's look at another example. All right, this is sort of the other option where we have an odd power on tangent. So when we have an odd power on tangent, you bring off a tangent and a secant here with the dx to make du, and let u be secant of x. U is secant of x, du is secant x, tangent x. Tangent square of x is secant square of x minus 1, so tangent square of x is u squared minus 1. So we left, after we split one of the tangents off, we still have an even amount of tangents left, in this case just tangent square, so it becomes u squared minus 1. With this secant to the 6th is u to the 6th, and all this back in parentheses is secant x, tangent x, dx is all absorbed into the du. Distribute the u to the 6th, this becomes u to the 8th minus u to the 6th, and now we can just find an antiderivative by using the power rule. Go up 1, it's 9, multiply by that reciprocal, puts a 1/9 in front. This power goes up to 7, multiply by 1/7. Then we got to put a plus c when our last integral sign disappears. Here I factored out, like I did the last one, I factor out a 1/9 and a 1/7 and a u to the 7th. 1/9 times 1/7 is 1 over 63. Again, kind of like getting a common denominator. And what's left, well, we're basically multiplying by 63 and dividing by u to the 7th for what goes in here. 63, we're basically multiplying by 9 and a 7. The 9 cancels and we're left with a 7. And then this and this cancels, leaving a u squared. Here the u to the 7th cancels all together. This time the 7 cancels and we're left with a 9. So it's negative 9 there. And then plug back in secant of x. So one way to write it is 1 over 63 secant to the 7th of x, parentheses 7 secant square of x minus 9, close parentheses, plus c. Of course, there are other ways to write this in terms of cosine or some other trig identities we can apply, but that's a good version for the answer there. They have the answer here in cosines. So, but if you look at it, you can tell pretty well what we've got here. if you were to distribute this, so there's the 1 over 63, same as we have here. There's the 7. So here if we look at 7 over cosine of the ninth is a secant to the ninth, which is basically the u to the ninth here. Or here, if we distribute these two with the 7, so that seems to be the same. And a cosine square over cosine of the ninth is a cosine of the 7th in the denominator, which is a secant to the 7th times the -9, which is what you get if you multiply that -9 times that secant to the 7th. So this is, in fact, the same function with the same c even. Right now c is 0, but of course it could be anything. You could see the graphs there. All right, here's another one. If we got tangent square, what we do is we just apply the identity right away to make this secant square minus 1. And now we have two integrals. One's just a constant function, so that just gives us an x. And the secant square is just the derivative of tangent x. So tangent x is our antiderivative. Now, before I go any further, you got to be a little careful here. This is a trig function, and tangent is not defined everywhere. It has some discontinuities in some places where it's undefined. But from 0 to pi over 4, tangent of x is defined, so tangent of x and then square it is defined. So this, and it's continuous where it's defined. So this is continuous on this closed interval from 0 to pi over 4. So it is legitimate to do the fundamental theorem of calculus here. If there had discontinuity in here, we would have to be a little bit more careful with that. We would have an improper integral. So going back to this, we found an antiderivative. Since it is appropriate to do this, we can apply the fundamental theorem and says, okay, once we found our antiderivative, just evaluate the endpoints and subtract. And that'll give us an exact value for a definite integral. Put in pi over 4 here and here, minus, put in 0. 0 is 0, tangent of 0 is 0, so these two terms just go away. Pi over 4 is not much we can do with that, but tangent of pi over 4 is just 1. So the exact answer is 1 minus pi over 4. Or if you'd rather get it as a common denominator, I guess it's 4 minus pi all over 4. And approximately in decimals, that's 0.2146. And you can see that the antiderivative that we got here is the same. This is a definite integral. Because I couldn't get we wouldn't put in exactly pi over 4 here. The exact value is not exactly right, but the decimal approximation is what we have here as well. And it's illustrated by this area right here. So the blue graph is the tangent square of x. And if we just go from 0 to pi over 4, which is right here, we get this green area. And this area is 1 minus pi over 4, or about 0.2. When you're not sure what else to do, and all else fails, change things to sines and cosines. Here's an example where that could be useful. Secant of x over tangent to the 6th of x. So if we let u be sine of, well, switch to sines and cosines first. So secant of x is 1 over cosine of x. Tangent of x is sine over cosine of x. And then we're going to raise to the 6th power. So let's see. We end up with a sine to the 6th in the denominator, which is sine of x to the -6. This cosine to the 6th of x gets flipped off to the top, cancels out one of them with that, so we get cosine to the 5th, and I'm going to split it off as cosine to the 4th of x times cosine of x. Since I have an odd number of cosines, I want the cosine of x to be part of the du, which means u is sine of x. So let u be sine of x, du is cosine of x dx. Cosine square of x is 1 minus sine square of x, which is 1 minus u square. So I can take the cosine x dx, that becomes du. Cosine squared of x is 1 minus u square. So this is cosine square and then square again. So the cosine square for the base becomes 1 minus u square, and then you square it again. And then this becomes u to the -6th. Now we're going to switch this. We need to switch the limits here if we're going to change it to u. if we don't want to change back to x's again in the end. So if we let x be pi over 6, we go plug it back in here, and we see that u is pi over sine of pi over 6, which is a half. And if x is pi over 3, u is sine of pi over 3, which is square root of 3 over 2. This comes from one of our basic triangles, our pi over 6, pi over 3, pi over 2 triangle, or 30 degree, 60 degree, 90 degree triangle, which has sides of length 1, square root of 3, and hypotenuse of 2. Okay, so that changes our limits here once we change to u. Now we don't have to change back to any more trig functions at this point. It's all algebraic stuff here. So I'm going to square this out. Square the last, that's u to the fourth. Square the first, that's 1. Multiply and double for the middle term, minus 2 u to the square. Distribute the u to the negative 6. U to the 4 times u to the negative 6 is u to the negative 2. U to the 6 times u squared is u to the negative 4. That's times our negative 2. And multiply by 1 here, we get u to the negative 6. Now we can do our antiderivative. Okay. And let's see here. Use the power rule. This goes up by 1 to negative 1. Divide by that, which puts us a negative 1 here. This goes up to negative 3. Add 1 to the power. Negative 4 plus 1 is negative 3. Multiply by the negative 1/3 times negative 2 is positive 2/3. This one, negative 6 plus 1 is negative 5. Multiply by negative 1/5 times 1 is negative 1/5. Evaluate from 1/2 to the square root of 3 over 2. By the way, we should note, let me check something here. So that should have been a definite integral to begin with. And notice that the integrand, this function here, is continuous on the interval of integration. So if you go between pi over 6 and pi over 3, those are strictly first quadrant angles. All the trig functions are defined there, and they're not 0. And so this is going to be defined and continuous. Okay, so what we're doing here is legitimate. Okay, so where were we? We're to this point where we've found an antiderivative. Let's clean it up just a little bit before we start substituting. I'm going to change it to fraction form. This is negative 1 over u. This is 2 over 3u cubed. This is 1 over u to the 5th. Okay, I'm going to get a common denominator. We're going to get a u to the 5th. We're going to get a 3 times 5 is 15. So this first one, to get that, we're going to multiply top and bottom by u to the 4th. So that gives us that. We're going to multiply top and bottom by 15. So that gives us a negative 15. For the second one, we're going to multiply by u squared in the top and bottom. So that's why we have a u squared there. And we're going to multiply top and bottom by 5. 5 times 2 is the 10 that we got there. And the last one, we're going to multiply top and bottom by 3. So that gives us a negative 3 in the top. All right, so we've got this rational function of u, and we want to evaluate it. Now, the arithmetic gets a little bit nasty from here because we've got a lot of fraction arithmetic, and we've got a square root in there. So let's just bear with me. So we take this, pretty straightforward. Just plug in the square root of 3 over 2 for the u's here, here, and here. And similarly, plug in a half here, here, and here. Okay. Now we're going to go ahead and just raise all these powers. Okay. 2 to the 4th is 16. Square root of 3 times square root of 3. Square once, square root of 3 times square root of 3 is just 3. And square it again, that makes a 9. So this is 9/16. Square root of 3 squared is 3. 2 squared is 4. So this becomes 3/4. 2 to the 5th is 32. So you get a 32 there. 4 of these square root of 3's we already said was going to be 9, and then we got one more. So this is 9 square root of 3. Similarly over here, 2 to the 4th is 16, 2 squared is 4, and 2 to the 5th is 32. So we're at that point. Now we have fractions inside our fractions. That's just not right. That's just too nasty. So we're going to get rid of those by multiplying top and bottom of each fraction by 32. All right, let's see what happens here. When we multiply this one by 32, the 32 goes away. We got our square root of 3, and we got 9 times 15, which is 135. We multiply this one by 32, that cancels, just leaving the 15. Now we got to distribute the 32 here. 32 times negative 3 is negative 96. 32 divided by 4 is 8. 8 times 3 is 24, times 10 more is 240. 32 divided by 16 is 2, times negative 15 is negative 30, times 9 more is negative 270. Here I'm going to distribute the negative up here as well as the 32, so I made this plus in here in the beginning. So it changes all the signs from negative, positive, negative to positive, negative, positive. Okay, so let's see, we're distributing the 32. 32 divided by 16 is 2, times the 15 is the 30. 32 divided by 4 is 8, times the 10 is 80, and 32 times 3 is 96. And I already talked about the signs. 32 cancels out, leaves the 15. Okay, now let's combine some like terms, or just add the numerators up. If you add negative 270 plus 240, that's negative 30, plus a negative 96 is negative 126. 30 minus 80 is negative 50, plus 96 is 46. I'm going to rationalize the denominator here by multiplying by square root of 3 over square root of 3, leaves a 3 here and a square root of 3 in the top. But there's also some 3's that we can cancel out here. Notice that 6 plus 2 plus 1 is 9, so that's divisible by 9. 5 plus 3 plus 1 is also 9. So we can actually cancel a 9 out here first. And then that leaves 14 in the top. And then we have the 9 we canceled out here, but then times the leaves 5 here. Let's see, that leaves out 15 here. And then we got the other 3 because square root of 3 times square root of 3 is 3. So this rationalizes the denominator and also reduce that fraction. 46 over 15 doesn't reduce. So that's one good way to write it in an exact form. Plug that in a calculator and you can get about 2.5. 2.527880415. And let's check it with the and illustrate it with GeoGebra. Using my GeoGebra app, I did it here. Secant of x divided by tangent to the, what was it, 6th of x. And I typed in pi divided by 6 here, and pi divided by 3 here, but of course these are approximations, which means this is kind of not correct. But this decimal is a correct approximation. Here's the antiderivative. They did something weird here. They didn't cancel the 2 and the 30. But if you look at it, that's the same antiderivative that I got here if you just replace all the u's by sine of x. Of course, we're not trying to find the antiderivative. That was just a means to an end on this one. We wanted to find the actual definite integral, which is this area here. So this function is blue, and on this interval it's positive and decreasing here, and the area under there, that is that green, and that is well, it's this. It's 46 over 15 minus 14 square root of 3 over 45, or about 2.5. Okay, I think I'll show you one more kind in the next video, and then that will kind of wrap us up, I think, for some trig functions.